YouTube. So today I'm taking a request from Lala. It's number 14 from chapter 7, and that section is on, so this is on the section about the natural response of an RL circuit. By the way, you guys, I want to thank everybody out there that is sharing videos that are getting help. So make sure that you're not that guy that comes, watches a video, gets help, and then doesn't at least like the Facebook or share it with your classmates. Because it's, for this channel to grow, it really pretty much has to be by grassroots efforts. So please get the word out there by sharing videos that you like or got help from, or liking the Facebook page, or liking a link on the Facebook page, because the more people that come, it's going to benefit you. You'll get more interaction, you'll get help from other students in other parts of the world, and that's my goal. I really want this to be more of an interactive site of people helping each other, and that's just going to be a result of more people discovering, so please help. Okay, so problem number 14 from chapter 7. We have a 120 volt independent voltage source in series with a 40 ohm resistor. 60 ohms there, 6 there. The switch is closed at time 0, and then at time 0 it opens. And it disconnects from an inductor of 250 millihenries, a dependent voltage source that is controlled by the current through the 60 ohm resistor, and that is in parallel with a 100 ohm resistor. So we're looking for a general equation for the current through the inductor. So let me give you the direction. So current through So this is the current through the inductor, IL. So we're looking for that general equation. We're looking for the general equation after the switching happens for the voltage drop across the inductor. We're also looking for the general equation for the current that controls the voltage source. So let's get started. The first thing you always have to do is you have to look at the circuit before the switching happens and the circuit as time goes to infinity. So the switching before the circuit happens is going to be the initial condition. The circuit at time of infinity is going to be the DC steady state. So let's look at the easier case. The easier case is when after the switching happens. There's a certain amount of energy, initial energy, stored in the inductor, and you can see that it's not connected to any other independent voltage source. And so what's going to happen is all the energy is going to dissipate through the resistors, and eventually everything will go to 0. That's the steady state condition of this circuit. So that's the easy part, the disconnect. Now let's look at the circuit before the switching happens. So we got this, which is closed. Let's draw this. So we have a 120 volt independent voltage source. It's connected to a 40 ohm resistor, and that's connected to a 60 ohm resistor. We got 6 here. Here's my switch, it's closed. My inductor is a short in this DC steady state. So, and then we've got some kind of current flowing through there. And so this voltage is providing a charge, so it's charged this up to its steady state, and some current is looping through that. And we need to find that current. In order to do that, we're going to source transform this right here to find its current equivalent. So 120 in series with 40 is going to be 3 amps. So I'm going to replace this with 3 amps in parallel with 40. I got 3 amps going like that, and that's going to be in parallel with 40. So let's rethink this circuit. So now I have 40 in parallel with 60 in parallel with 6. So this is right here, just really a parallel connection because our inductor is a short. And we don't need to worry about the rest of the circuit, by the way, before the switching happens. The reason is because the inductor is a short, so it's like the rest of the circuit doesn't exist. It shorts it out. So, so now what we have here as far as equivalent resistance REQ, that's going to be 40 in parallel with 60 in parallel with 6. Okay, so then this reduces into, and that is going to be, so the equivalent resistance is going to be 4.8 ohms. So remember, go back to chapter 3 when we talked about current division. Current division says that the current, this current is going to split. It's going to come down here, it's going to split 3 ways. The current through the branch that we're interested in is going to be the equivalent resistance, so IL is going to be the equivalent resistance divided by the branch that we're interested in which case we're going to call this R6 ohms, right? So that resistance, that's the branch that we're interested in, and that's going to be times the total, I total, okay? So in our case, that's going to be 4.8 ohms over 6 times 3 amps. All right, so that should give you a value of 2.4 amps. 2.4. That's going in this direction. Since our schematic is specifying going towards the ground, we're going to stick a negative in front of that. And that will specify that it's going towards, if you're going to specify that goes towards the ground when it really goes up, then we'll stick a negative in front of that. So that's going to be our I initial. So let's call that I, current through the inductor at time 0. I of 0 is negative 2.4 amps. We need that information. Actually, I'm going to call this, I'm going to label this in accordance with the book. I call it I naught. So let's call that I naught. That's the current before the switching occurs. Okay, so now we have that critical piece of information. The next thing we have to do is we have to pull on a relationship in between initial current and the general equation. So the general equation of our inductor, I of t, the general equation is going to be the initial current before the switching happens, e to the negative r over L. Notice that r over L is tau. So that's going to be t amps. That's our general equation. We know that. We need to find r over L. So let's consider the circuit after the switching happens. After the switching happens, we have, I'm going to redraw this because now we've gotten all the information we need from the initial condition. We don't need it anymore. So let's just consider now the switch has happened. It's completely disconnected from that part. What is the R? The L is pretty easy, right? That's 250 millihenries. But what's the R? Well, is it this R? Is it this R? As it turns out, the R is going to be the resistance, the total resistance seen by the inductor. And we can't simply say it's going to be 100 in parallel with 60 because something is going on here. And so we can't just reduce it to 100 in parallel with 60. So what we have to do then is drop back on chapter 4 or chapter 3 or 4 where we learned about Thevenin equivalence, because the Thevenin equivalent number is when we open the load. So we open something that we're interested in finding, and then we look at what does, no matter what, how many N circuit elements there are, what is the single resistance seen by the load? And then what is, so that's what we're going to do. That's going to be our Thevenin. So we're looking for the Thevenin equivalence here. So this R is really our Thevenin. It's always our Thevenin. And if you have anything other than resistors, you have to use your draw back on Thevenin's, your training on Thevenin in order to find that R. Always it's our Thevenin after the switching happens. So in this case, let's open the load. Our load is, and notice that we, think back on our Thevenin. Remember, V Thevenin is equal to I short circuit times R Thevenin, right? So we're looking for R Thevenin. We already have I short circuit. So I short circuit is going to be that 2.4 amps that we found. So I short circuit is the short circuit current that's flowing through the load. In this case, that if we were to short the load. So if we were to short the load, we would have 2.4 amps. So now let's find, let's redraw that. We're going to open the inductor right here. This is our V Thevenin, right? So now we got plus minus 20I delta, and then we got 100 here, and then we got 60 here. And so how do we find V Thevenin and I Thevenin? Well, we have to use the node voltage method or the mesh current method, but so we could have used the shorted this out and then said, okay, I have 2.4 amps. That would work as well. But I'm going to choose the node voltage method, which works equally well. I'm partial to the node voltage method. I don't know why. Just am. So I have some V sub x, and I don't know what it is here. So I'm just going to go ahead and apply the node voltage method there. So what we're going to do is we're going to define this constraint equation. So we have a constraint equation here, and that's going to be, we have a voltage drop plus to minus means it went down in potential. So V Thevenin minus 20I delta is going to be V sub x. So V Thevenin, that's our one equation that we have, minus 20I delta is equal to Vx. This is our I delta. So the second constraint equation that we have is going to be negative I delta, or I delta is going to be negative Vx over 60. Okay, so then we need to write an equation here. So naturally we're going to take that to be the ground. This is an open, so there's no current there. So this is going to be node voltage at Vx is going to be Vx over 100 plus Vx over 60. KCL. Actually, my bad. We need to write KCL, current through KCL like that. So we know the short circuit current is going to be, this is negative, going towards the ground is going to be the negative 2.4 amps. So that's going to be negative 2.4 plus Vx over 100 plus Vx and plus Vx over 60. So this current right here. And actually, let's go ahead and solve for this current. So we know, well, let's just go ahead and do plus Vx over 60. That's equal to 0. So then we bring the 2.4 on the other side. I got Vx 1 over 100 plus 1 over 60. That's equal to 2.4. Alright, so divided by 100 plus 1 divided by 60, and then 2.4. So this is telling me, when I solve for that, I find that Vx is really 90 volts. Okay. So now that I know what Vx is, I can solve for V Thevenin. So V Thevenin is, and also 20I delta. So I delta is 90, so negative 90, so it's going to be Vx, negative Vx over 60. And that's going to give me negative 90 divided by 50. That gives me negative 1.8. Let's put that over here. So I delta is negative 1.8. That's immediately after the switching happens, negative 1.8 amps. Okay, so now we know Vx. That was really important. Now we need to figure out V Thevenin. So and the reason we need V Thevenin is we need R Thevenin, which is going to be V Thevenin divided by I short circuit. So V Thevenin then is negative, so it's going to be Vx plus 20 times I delta. So that's going to be 90 plus 20 times negative 1.8. And that is going to give me, so Vx, so then we have, so we got 20, so 90 minus 20 times 1.8 gives me V Thevenin. Okay, so 90 minus 60, 20 times 1.8. Vx minus 30. Hang on, you guys, I have a mistake somewhere for finding V Thevenin. Okay, so 20 V Thevenin. So 20 I delta. So 20 times I delta, so 20 times 1.8. Oh, I delta is, I delta should be, I delta is 37. Vx over 60, so Vx is 90 divided by 60. Oh, that's because I had a typo on my calculator. So I said I delta is 90, negative 90 over 60, and then I said that was 1.8, and somehow I typed it wrong in I did 90 over 50, so it's actually not 1.5, which is why my math isn't working out. It's really negative 1.5 amps. So then I have negative 1.5 here. So let's see, negative 1.5. So then 90 minus 20 times negative 1.5. Okay, 90 plus 20 times negative 1.5. Okay, now my math matches with that. So 20 times negative 1.5, so this tells me V Thevenin is 60 volts. Okay, so now I know what V Thevenin is. So I know that 60 volts is equal to 1.5. I short circuit is 2.4, and that's times R Thevenin. So R Thevenin is going to be 60 volts divided by 2.4. So 60 divided by 2.4 is going to be 25 ohms. So R Thevenin is 25 ohms. So that's what the, so that is the resistance seen by the inductor. It sees 25 ohms out of all of that. So now we know what that is, we can use our equation to find the part A. So part A is I, current through the inductor after the switching happens. Well, that's going to be initial current before the switching occurs divided by negative R over L, which by the way is tau, amps. Okay, that's going to be after the switching occurs. So let's fill in the blank. R over L. R is 25, L is 2 250 millis, so that's going to be 100, I believe. Okay, so then what we got here then is going to be, the answer for part A is negative 2.4 e to the minus 100 t amps. That's the formula for, that's the general equation for current through the inductor after the switching happens. Voltage is just IR, V is equal to IR, so we're going to go, we're going to use, because we're going to use V is equal to L di dt, that relationship. So remember from chapter 6 we have V is equal to L di dt. So V equal to L di dt. So that's going to be 250 millihenries times d I dt is going to be, this is I, so it's going to give me negative 2.4 times negative 100, and all that's going to be times negative 100 e to the negative 100 t amps, and that, or volts. So, so then we're going to go 250 e minus 3 times negative 2.4 times negative 100, and that's going to give us 60. So the answer for part B is 60 e to the minus 100 t volts. That's a general equation for the voltage drop across the inductor after the switching happens. And then for the final one, current through the 60 ohm resistor, that's just going to be the negative 1.5, so that's going to be negative 1.5 e to the minus 100 t amps. Okay, you guys, that is the answer to problem number 14 from chapter 7. So again, please share the video or like the link on the Facebook if you got help. So that is one way that you can easily help the channel out without doing a heck of a lot. All right, good luck, you guys.